Hey guys, welcome to another math video. We're going to continue talking about similar triangles today. So last time we looked at naming triangles, sides and angles. We also learned how to identify corresponding sides and angles. And finally we saw how to figure out the measure of a missing angle in a triangle. So this is stuff we did last time. And last time we were told that all the triangles were similar triangles. Right off the bat we'd say, okay, these are two similar triangles. What we're going to do today is learn how to determine whether two triangles are similar or not. So there are two ways to check to see if two triangles are similar. So this is the first way. You have to check to see if every pair of corresponding angles are equal. So what this means is that if you know or can figure out all three angles on both triangles, and each triangle has the same three angle measurements, then the two triangles are similar. So let's take a look at an example. It'll make a little bit more sense. Okay, so we want to make sure that all three angles here and all three angles here are the same. Then these two triangles are similar. All right. So we need to figure out this angle here and this angle here. So again, we add up the two angles we know. These add up to 150, and then we subtract 180, which is all three combined, subtract 150, and we get 30 degrees. Okay, so right away we could say, okay, well, I know I have a 40 and a 30 here. I have a 40 and a 30 here. There's only one option for this angle, right? And that option is to have this one as 110. Right, so you can say, okay, yes, these two are similar, because once we figured out this was 30, then we knew these two are the same, and these two are the same, which means the last ones also have to be the same. So I'd say yes. And if you wanted proof, we could go, okay, these two add up to 70, so I go 180, subtract 70, I get 110 degrees. So yes, that is true. How about this one here? Again, we need to find the missing angles, this one here and this one here. Do the same thing. Okay, so we go 50 and 80 is 130. So I go 180 subtract 130, and I get 50 degrees. Okay, so I have 80, 50, and 50. On the other one here, I have 80 and 45. Right away, so I can see, okay, I needed this one to be 50, and it's not. So I can say no. These two triangles are not similar. Now here is the second way to figure out if they are similar or not. Each pair of corresponding sides would be enlarged or reduced by the same scale factor. Basically what we're saying is that all the sides are proportional to each other. So what this means is that you have to figure out the scale factor for each corresponding pair of sides. So again, that's by using this fraction. Length on diagram is always on top, length on original is always on the bottom. So put the numbers into the fraction above for all three corresponding sides. If they all have the same scale factor, then the two triangles are similar. So for example, what are the following pairs of triangles similar? Okay, so we want to compare the long side to the long side, short to short, medium to medium. So the long side, we read, is 36 and 8. Short side is 3 and 13.5. And the medium side is 31.5 and 7. So again, since this is the diagram, this is always on top. This is the original, it's always on the bottom. Okay, so I'll start with the short sides. I'll go 13.5 divided by 3. Get your calculator, go 13.5 divided by 3. You get 4.5. Okay, then we'll do the same thing with the long sides. We have 36 over 8. Again, simple calculation, 36 over 8, 4.5. So far, so good. And let's check the medium side. So I have 31.5 over 7. What do I get? 31.5 over 7 equals 4.5. So since comparing all the corresponding sides gave me the same scale factor, I would say yes, these triangles are similar. All right, so another example could look like this one here. Determine if the following triangles are similar. So again, we're not told which one's the diagram, which one's the original. So you can pick which one's on top, which one's on bottom. It's usually a good idea to have the larger numbers on top, the smaller numbers on the bottom. So that's what I'll do. I'll say this triangle's on top, this triangle's on the bottom. Okay, so let's start off by comparing these short sides. So go 6 divided by 4. And what do I get there? 6 divided by 4 equals 1.5. Then I'll compare the long sides, which is 6 and 9. Again, 9's on top because it's bigger. 6 is on the bottom. So 9 divided by 6 equals 1.5 again. So far, so good. And the medium sides is 7.5 and 5. 7.5 and 5. What do I get? 7.5 divided by 5 equals 1.5 again. So again, all corresponding sides give the same scale factor. So yes, the triangles are, in fact, similar triangles. So we can also use what we know about similar triangles to solve problems, to solve word problems. If we can figure out that two triangles are similar, we can use what we know about to find the missing side lengths in a problem. So let's take a look at some more examples. So for example, at a certain time of day, there's a person who's 1.8 meters tall, 1.8, has a shadow that's 1.3 meters long, 1.3. At the same time of day, a totem pole has a shadow that's 6 meters long. The question is, how tall is a totem pole? We want to round to one decimal place. Well, the first thing we need to notice is that the angle between the sun's rays and the ground, here and here, will be the same for both the totem pole and the person, because the sun is shining down on them at the exact same angle, right? The sun is so far away that it gives the same angle here and here, so these two triangles are similar. Again, we don't know which one's the diagram, which one's the original, so like I said, pick the bigger numbers to be on top of your fraction. So the totem pole will be on top, the person will be on the bottom. Okay, so we know that the shadows can be compared to each other. So we can go 6 compared to 1.3 and see what we get. 6 divided by 1.3 equals 4.615. So now this is the scale factor. This is how many times bigger the totem pole is than the person, because that's how many times longer the shadow was than the person's shadow. So I can take the height of the person and multiply by the scale factor by 4.615. Now you need to check to make sure this answer makes sense. If it doesn't, try dividing instead, but I'm going to try multiplying first. So I go 1.8, height of the person, 1.8, and multiply that by 4.615, and I get 8.307. I said to round it to the nearest, round to one decimal place, so I'll say it's 8.3 meters tall. Okay, so that's the type of problem that we can solve given that these two are similar triangles. We're going to take a look at one more example. We're going to skip the last one just because I'm running out of time. If you want to see this one, I can do it in class for you. That's this one here, but I'm going to skip that one for now. So another example, a surveyor wants to determine the width of a lake at 2 points. So from here to here is the width of the lake that they want to figure out. She measures the distances and angles on land that were given here and sketches this diagram. So we want to determine the distance across the lake to the nearest meter. Okay, so I'm going to draw the two triangles that I have. The big one here, sorry if it's not perfect, is H and J. Okay, and then the small one is about this size. Again, the point here is J. It goes from P to Q. So again, there's kind of picking random letters. That's okay. And I can figure out the lengths that are given here. I know that this one is 210 meters long from J to P. Now from J to H, I need to go 210 plus 305 more. So it's 305 and 210 give me 515. So this one here is 515 meters long. Okay, and I also know that right here is 230 meters. So again, I know the side here corresponds to the side here, and I know that this one corresponds to this one. So again, they don't tell you which one's diagram, which one's original, so pick the bigger one to be on top of your fraction, and then this one will be on the bottom. Okay, so I need to compare this here, 515, to the side here, 210. And what do we get there? We go 515 divided by 210, and I get 2.45. Again, the more decimal places you put, the more accurate your answer will be. So I take my scale factor. That means that this one here is 2.45 times bigger than this one here. So then I can multiply this by the length up here. So 230 times 2.45 gives me, I still have my calculator here, 230 times 2.45 equals. Set to the nearest meter, so I'll say this equals 564 meters across the lake. Alright, so that's all for today's video. If you want me to do this last example in class, I'll leave it on your notes, but I'm not going to do it with you on the video here. You can try it on your own, and then we'll compare your answer to mine in class. Have a great day. Thanks a lot.